All right, so let's get started. So the same as previous, we'll go through several Q&A. So the first one is like folks are asking about like caches for bypassing patch cache, because I think the point is like using patch cache, we can accelerate the time to get a file from a storage device. Because if the file are cached in the patch cache, then the application doesn't really need to read them from a storage device. But there are several cases that the the application designers will avoid using patch cache. So first one is called direct IO. So direct IO usually like using some database, because for some like large application like database or like some machine learning application, those kind of stuff, they can have their own user buffer. In that case, using patch cache will not really benefit, because like if you open the patch cache, then for each of the file requests, you need to get the data from patch cache. And in that case, if you are an user process, then you need to interact with the operating system very frequent. So in this case, if the application, for example, it can say, I want to get a super large memory, and the application can manage the memory by itself. In that case, it doesn't really need patch cache. So the application can directly use a direct IO to get the data from the storage device. And the second one is the synchronous IO. So the idea behind synchronous IO is because the consistency issue. Like if we use a patch cache, and if in some cases, for example, the power shortage or like the operating system crash or like the system crash, then there are a very low probability the cases the data doesn't really sync with the storage device, because if you write the data, in most cases, if you have patch cache, the write operations will first modify the data in the patch cache, but will not directly modify the data in the storage device at that moment. So using synchronous IO, you can update the data both in the patch cache and the storage device. But in that case, it doesn't really take the advantage of the patch cache. Okay. But the good thing is you can make sure 100% of consistency. No matter the system crash at any time, you don't really need to care about the consistency, because every time you update the data back to the storage device. Okay. So the second one is about NAND flash SSD. Like someone is asking about like, actually there are several issues NAND flash SSD will face, like write amplification and like lifetime issue. And actually the SSD controller inside the SSD can take care of. And there are some special cases. For example, some cases like operating system can help. For example, currently there is a command named the trim command from operating system. And the trim command is, the main idea behind the trim command is to send the hint. For example, if a user delete some files, then the trim command can send those information to the SSD controller. But without this operating system support, SSD controller can still take care of also like all of the challenges in SSD. And this is why we need SSD controller. So we don't really need the operating system support or like even the application support, and SSD can do the things by itself. And this idea is also same for the SMR, because like SMR needs to do the sequential write operations. So it will also face the challenge that SSD face, just like garbage collection stuff. And actually, operating system doesn't really know you are using SMR or hard disk drive in most cases. So operating system will not really customize a garbage collection for the SMR. And in this case, SMR should have their own controller to run the garbage collection. Okay. So usually most of the storage device, if they have their spatial constraints, in most cases, they will have their own firmware to deal with this kind of constraints. Doesn't really need to bother the operating system. Okay, So I think there is a very interesting question is about as hard disk drive density increase. I mean, because if it is possible to reduce the track wide, then you can increase the density of hard disk drive, right? So in this case, read head will face several issues because for each track, if it becomes narrow, then the read head will face the weaker magnetic signal interference, and mechanical precision is hard to be controlled. So it does increase the challenge for read head. But I think for current manufacturing technologies and HDD technologies, most of these issues can still be handled. Okay. So the last one would be the QLC compared with the MLC and SLC NAND. Because let's first do some record, like using QLC or like using MLC, it means like in the same cells, you are going to decide 3 bits or even 4 bits. So for 3 bits, it means you need to decide for 2 to the 3, like add labels. And 4 bits means you need to decide for 16 labels inside one cell. So the things will be like this kind of stuff. Like right after programming, you will get like 4 possibilities for the 2 bit cells MLC. So because using almost the same voltage value, like from 0 to VT, actually you need to decide more labels here. So it does increase the challenge for how to precisely control the voltage, and like if there's error, then how to deal with it. The error occurs because like look at the figure again. If there are some retention errors, then probably each of the package here will become loosey. I mean, loosey is this is a tight and this is a loose. The red one is a loose. So loose means like because there are some error, so it looks like this. And then for 1, 0, 0, 1, and 0, 0, you can see in a picture like there are some portion of the possibility it will cross the reference voltage. So for this area, and this area will be misjudged. For example, if the data if the voltage in this area and we read, it is possible to read the data inside the cell, then it will be judged as 0, 1, for example. But actually here for this kind of cells, actually there are 0, 0, not 0, 1. So there is a misjudge here. And this is the reason we say for MLC or even QLC, because there are more cells, so even very few retention loads, it will make the read process becomes harder to read out the data. Okay. So this is about the narrow margin issues here. Okay. But actually, we did not cover this so deep in this class. So if you're interested in, we will have a class talking about this kind of stuff in the next semester. Okay, and the other thing is about the hard disk drive part. So last week, some of you are asking about the zombie recording. So I just moved the slides for from the next semester to here. So this is our plate, right? This is one plate, and on the plate there are several sectors. So the number means the sector ID, and this is the outest track, and this is the innerst track. So you can see the size for the sector on the outest track is quite, I mean, will be like 2 times or even 3 times larger than the sector in the inner track. Okay, but in general, I mean, if we don't use a zombie recording, in general, they are all 512 byte. So I mean, like for this sector, even it has larger space, larger area in the physical perspective, but it can only store like 512 byte. So it wastes some of the physical capacity here. So a better way is about to store more data on the outer track. So like this, actually, if compared with the size, actually this size would be very close to this size. So actually for the outest track, actually for this region, we can store like three sectors in this outer track. Okay, so it means like for the data density, we can store like in this example is 3 times more data in the outer track compared with the inner track. Okay, and then the throughput will definitely increase because actually the spindle like here and it's swiped from the left hand side to the right hand side. So for a time unit, actually it can read out more data compared with the inner track. Okay, so using the zone B recording, it does increase the throughput of the SSD. But actually there are okay. So the reason like it calls zone B recording is because in this example, like the middle circle means the traditional one. So this is the disk track, and for each track there are sectors on it. But if we are going to use zone B recording, then we will partition the tracks into several zones. So the outer zones means like we will increase the density of the track. For example, outer zone means we can store more the data in the outer zone, and the inner zone, like you can only store fewer data inside. So there are some here, like for zone 0, then there are 15 sectors per track. But if you are in the zone 6, then you only have 6 sectors per track. Okay, so one zone is possible to include like 2 or even 3 tracks inside. And this is all good things for a zone B recording, but there are also bad things. Bad thing is about like if we're going to use a zone B recording and when we are going to do the address mapping here, and the issue will be you need different address mapping, or like even you need some extra, I would say like insignificant extra space to record about, okay, so which tracks are in zone like zone 0 and which tracks are in zone 1. Okay, but if you are using a traditional one, you lose the high throughput, but you don't need to have this kind of complex addressing here, because for each track, the number of the sectors on it will be the same. Okay, so this is about the zone B recording stuff. Okay, so let's first do some recalls on the hard disk drive and solid state drives, and we still have one slide left for the SSD. Okay, so for the hard disk drive, the same example, like this is our plate, and there are several sectors on it. So actually, the disk performance, there are 3 main factors here. The first one is seek time. So seek time is about the distance to move the read head from like this, from the inner to the outer, or outer to the inner. This is about seek times. So because seek times involves the disk moving, so disk movement is a mechanical moving, so it takes slightly long time, like 4.9 milliseconds here. And then rotation is about the time to rotate the plate. Okay, so the rotation, like if you're going to buy an hard disk drive, then you will see like there's called RPM stuff, and you can calculate how fast it is for each run. And the third one is a transfer time. So transfer time is to rewrite data to the surface. Okay, so use the GMR to read the data, or like to use the write head to write the data. It takes sometimes. Okay. Okay, so we also talk about the random access and sequential access. The key thing is about for the seek times, like if you're going to frequently move from inner to outer, outer to inner, it takes time. And also, if the data is not aligned with the rotation directions, then it also takes time. So sequential access also always has a good performance for the hard disk drive. But if it is random, then it takes longer time. And actually, I also read a question is about like, is it possible to control a random, or like to control the access pattern? And in most cases, access patterns are decided by the user or applications. So it is not easy to say like if this is, for example, a random access, and in the systems, I mean in the OS systems or in the hard disk drive, we try to make the random access become sequential. It is hard, but I mean if there are some like power cache inside, and then if you are going to do some scheduling, then maybe it is possible, but not for all the cases. Okay. So also like we talk about how to really read and write the data from the hard disk drive. So this is a track, and on the track there are several sectors. Okay, so in the sectors, actually, there is a things called recording medium. So each recording medium you can think about is called 1 bit. Then each head, each hard disk drive head, it comprises the read head and the write head. So read head is using the technology called GMR, and write head is inductive write. So the size of the head is different. It differs a lot. So how to store the data? Then how to access the data? So read head works like this kind of stuff. So image, this is the recorded medium, and this is our read head. And this read head comprises a free layer and a fixed layer. So actually, when we are going to read the data, it depends on the directions between the fixed layer and the recording medium. Because fixed layer is fixed layer, so the direction is static. And the recording medium depends on what kind of data you're going to store inside. Is it 1 or 0? Okay. So using GMR, when GMR kind of moved around this recorded medium, okay, then this recorded medium, because it already has the magnetic field inside. For example, in this example, the right-hand side is north and the left-hand side is south. So the magnetic field is from south to north inside this recorded medium, right? Okay, so when the GMR kind of moved across this recorded medium, then the magnetic field will sense the free layer. So the free layer will be sensed, and then the free layer will show these directions from the left-hand side is north, right-hand side is south. So actually, how to decide like what is the directions of the recording medium? Actually, it depends on the resistance value of the GMR, because when a GMR moves through the recording medium, the free layer is polarized by the magnetic field, and then we now fixed layer and free layer, they have their own magnetic directions, and in this case, they are anti-parallel. So anti-parallel will let the GMR shows higher resistance stat. Okay, so this is the characteristics behind the GMR. If the fixed layer and free layer, they show anti-parallel magnetic directions, then the resistance value will become high. So on the other hand, the fixed layer, again, is the same directions. And if now the recording medium now store the data like from the left-hand side is north and the right-hand side is south. So again, for the GMR move through this recorded medium, the free layer will be sensed. And this time is right-hand side is north, left-hand side is south. So in this example, on the right-hand side, the fixed layer and free layer, their magnetic fields is in the same directions, and we call them the parallel. So this parallel magnetic field will make the GMR becomes in the low resistance state. Okay, so actually the GMR will always, the hard disk drive will always give the voltage value for the GMR, and then you have the voltage and you have the resistance, so you can get a current value. So sensing the current value, we can know now GMR is in a high resistance or low resistance. And if in a high resistance, it means this recording medium is 0. And on the other hand, if the GMR is low resistance, it means like it is 1 now. Okay, so a simple way to know how it is a high resistance or low resistance, you can just directly decide about like if the recording medium and the fixed layer, they are in the parallel directions, then it will become 0. And if the fixed layer and the recording medium, they are in the anti-parallel directions, it will become 1. Okay, so this is about how to read out the data by using this magnetic field stuff. And the right hand is using the inductive write. I think you guys already know this in your like junior high or senior high school. So it is about given the electron, and when the electron moves through the wire here, then there is a magnetic field. So the magnetic field can change the magnetic field on the recorded medium. And this is a reason why we need a larger write head, because the how strong the magnetic field is depends on the size of the magnet itself, right? Larger magnet, then you can get the larger force. Larger force can override the magnetic field on the recorded medium here. Okay. So this is about how to read out the data and write data on the hard disk drive. And then let's move on to the solid state drive. Okay, so solid state drive, we introduce several stuff. One is about we break down the SSD. So given this is an SSD, so inside the SSD there are several components. First one would be there are several controllers inside. Okay, there are all microcontrollers, but there's usually not only one. There are several controllers here. So controller will take care of several stuff. We will give you an overview later. And in addition to controller, there are also a couple of DRAM on the SSD, and we'll tell you the reason why later. Okay, so actually next week we focus a lot about the right-hand side stuff, just like the NAND flash cells. So for the controller, actually, it will connect with several channels. So each channel will connect with one chip. So one chip, there are several dies on it. So in this example, there are 4 dies on it. So actually, die will be the minimum granularity to get the request. So for example, if you have a read-write request and then you send into the chip, actually you can send up to 4 requests that can be run concurrently. But if you send like add requests to one chip with 4 dies, then there are only always 4 that can run in parallel, and the other 4 they will be pending. So until one die finish their request, then the die can use to serve for the 5th one or like the 6th one. Okay. So inside the die, there are 2 planes. And then for each plane, actually there are 1024 blocks inside. And the block is the minimum granularity to do the erase operations. Okay. So inside each block, there are 512 pages. Okay. So pages is a page is the minimum granularity for read and write the SSD. Okay. And then this is the details about what is the circuit looks like inside the block. So actually, for each of this, it is a memory cell. And last week, we focused a lot of time on introducing the how to read, write, and memory cell like this. Okay. So what is a page? Sorry. So a page is about like a lot of memory cells that chain by the word line. So here you can think about, usually we say for SSD, the page size is like 4 kilobytes. So it means like we will have 2,000 or 4,000 of memory cells that chain by the word line. So it depends on it is SOC or MLC. Okay, so this is a patch. And this patch is not, it's totally different from the OS patch. So they have no relation for these 2 stuff. Okay, so several word lines, they combine together, we'll call them a block. So this area is a block. Okay, so next, do some recalls on how to read, write, and the NAND flash cells. Because I think last time I do a little bit too fast, so there are several questions after the class. So let me clarify now. So actually, this is a cell. This is one SSD cell. So the data is stored in the floating gate, and the form for data is about the electron inside the floating gate, and the electron will show different voltage value. Okay, so like high voltage value means like bit 0, and low voltage value like bit 1, like this kind of stuff. And like the bottom part is a P substrate. And then between the floating gate and P substrate, there is a dielectric layer. So dielectric layer works like an electrical insulator. Okay, so this one will be a wire and penetrate through the N source and N drain. Okay, and here will be another like wire here. And here is a control gate. So, sorry. So this memory cells, actually we rotate minus 90 degrees to this one. So actually, this is a word line, this is a bit line. And in this example, this is the word line, and this, the horizontal is a bit line. Okay, so how to do the program? How to write the electrons into the floating gate? Actually, we will apply a higher voltage called 20 volt. And actually, how much voltage it is, it depends on different SSD. And this 20 volt is just for an example here. Different SSD, different NAND flash, they will have different configurations, so the voltage will be different. So the only thing the same will be, if we are going to program, if we are going to write something in the floating gate, we need to apply for a large voltage on the board line. So we use 20 volt to apply on the control gate, and then we will give the 0 volt for the P substrate. Okay, so 20 volt is a high voltage, so it will make the electron inside the P substrate becomes delocalized electrons. They will become so excited, and because 20 volt give very enough of the energy to let this electron to cross through the dielectric layer. So this is an insulator, but if the voltage you give is enough, then the electron can jump into the floating gate. Okay, so this is about how to program it. Okay, and then how to read the data. Actually, we will use a lower voltage value also apply on the board line. And in this example, we use 2 volt. Okay, when you're using a 2 volt, actually in this example, because you use a lower voltage, so you can only make fewer electron on P substrate becomes excited. So in this example, you can only get 4 delocalized electrons in this example. Okay, but the thing is about 2 volt is not able to let this electron cross through the dielectric layer because the energy is not enough to make them become so excited to cross through the insulator. So it is not possible for those delocalized electrons to cross through the black one, the insulator. And then they will be captured from the end source and end drain. Okay, but the case is about because 2, in this example, 2 is too few for those electrons to create a current. Because for a current, it is more enough of the electrons to generate the flow. Okay, so 2 is not enough. So actually there will be no current to pass through here. Okay, so 2 is not enough. Okay, so here's no current. Okay, so the idea is about there's not have enough electrons, so we cannot read, sorry. So using the 2 volt, we cannot get the current at the end of this bit line. Okay, but there's another scenario. So the scenario is like this. We give the same voltage value called 2 volt here. Okay, but actually this cell doesn't be programmed before. Okay, so when you use 2 volt, you can make a little bit fewer more electrons to be excited. So actually even they are using the same 2 volt, but on the right hand side, because there is no electrons in the floating gate. So it means it doesn't, I mean, it means like the NAND flash controller doesn't program this cell before. Okay, so there are more electrons will become excited, and this delocalized kind of electrons, once again, they cannot jump into the floating gate because the 2 volt is not high enough to make them, to give them enough of energy to cross through the insulator. So they are once again be captured by the end source and drain. But this time, because they have more enough of currents, more enough of electrons be captured in end source and end drain, so it can generate a current. So from here to here. Then if you have a sensor at the end of the bit line, you can get a current. So with this current value, you can know, okay, so there is no electron inside the floating gate. But on the left-hand side, you cannot get a current. So you will know actually there is electron inside the floating gate. So with current, with electron, without electron inside the floating gate, you can define, okay, this one probably will be like bit 0, and this one like bit 1, like this kind of stuff. Okay, so the key idea behind this kind of reading stuff is because higher voltage value induce more electrons from the P substrate. And the number of excited electron is correlated to the voltage value. So if you use 20 volt, then P substrate will give you a lot, quite more. But if you use 2, then you can get very few. Okay, so we also give you an example for how to read out one patch, because in this example, there's only one bit cell. Maybe you're thinking about this is not realistic enough. So the example is like this. So one word line, we can have several memory cells on it. And in this example, let me just put 4 here. Okay, so patch 1, patch 2, patch 3, and patch 4. So for each cell, they have their own voltage value in their floating gate. Okay, so if now in this case, we are going to program patch 2. So actually, let's image like now for patch 2, we have 4 cells and they're all 1111. And we are going to program them to 1100. Okay, so this is from the user perspective, but actually from a circuit perspective or from an SSD perspective, actually in patch 2, actually it's about there are like 1.9 volt, those kind of stuff, because it is low voltage. Okay, so they're 1111. So if we are going to make this voltage change to 1100, then we are going to do this kind of stuff. We apply a strong voltage, 20 volt here, and then because we use 20 volt, so basically we will change all the voltage value for the four memory cells for patch 2, right? But actually we only want to program the last 2 cells, and the first 2 we want to make it the same. So the case is about we apply a voltage called inhibition voltage. So for this inhibition voltage, we can avoid this for the first 2 cells be programmed. Okay, so the idea is like this. Now the same things, we use 20 volt, and there are a lot of electrons becomes excited, and if there is no inhibitions, then those electrons will cross the accelerator. But because here is another outer force from the horizontal directions, so those electrons, before crossing the accelerator, they will be forced to move out from the engine, because here is another force, like 5 volt force, will make them hard to cross the accelerator. Okay, so this V inhibition is here. We apply on the bit line, so we can avoid those cells. They are not going to be programmed. Okay, so in this case, actually we only program the last 2 cells. Okay, so their voltage value increased to 3.1 and 2.9 because there are more electrons inside this floating gate. Okay, so this is about the program. And the case is about, so how to read out the data from one patch. So the same thing, if we are going to read out the patch 2, then we will apply a relative low voltage. So in this case, we apply the 2.5 voltage here. So we apply 2.5, and then the thing is about, remember, if there's no electron inside, then if we use a 2.5 volt, then there are several more delocalized electrons. They will be captured on the end source and end drain. So it is possible to generate current. On the other hand, if there are already electrons inside the floating gate and you use the same 2.5 volt, you cannot generate a good amount of the electrons to create the current. So there are very few delocalized electrons becomes excited. So end source and end drain, they don't have enough electron, so it cannot cause the current. So the thing is like this. We'll have a sense a read like the current sensing unit here at the end of each bit line. So for this sensing unit, for the first 2 bit line, we can get the current because if bypass it, we can get a current. But for this 2, actually we cannot get it because there is no current value here. Okay, so in this case, the current value will be quite low. So for the patch 2, what we can know is the first 2 is bypassed, and the last 2, there's no current here. Okay, so it's 1100. Okay. Okay, so erase granularity. Actually, we need to erase in a block granularity. And okay, so the reason is just about because for the P substrate, okay, here, for a P substrate, actually on one P substrate, there are a lot of memory cells on it. So one P substrate, it accommodates a block of the flash patch. So P substrate, when we are going to apply a strong voltage to do the erase, actually a block of the NAND flash cells on this P substrate will be affected. So this is the reason like why erase should be aligned with the block. Okay, but the thing is like this. if the erase size is larger than the write size, then we need to do the sequential write constraint. The reason is now we program the data from low voltage to high voltage write. Then if we are going to program this high voltage data back to the low voltage state, then the thing we are going to do is called erase. It is to move the electron from the floating gate out of the floating gate, right? So each time we are going to update the data, it means we are going to do the erase. But erase unit is larger than write unit. So we will not really erase the data in place or in this place. We will write it to the other place, okay? So this is an example. So if we have this kind of NAND flash patch program to this kind of bit stream, then if we are going to update the data in those bit streams, actually we cannot erase this patch, because if we erase this patch, it means we are going to erase the whole block. But we only want to update this patch and we don't want to update the other patches. So a better way is to copy out this patch and then write the data in a DRAM or somewhere else, not in this block. Then write back to the SSD to another like patch, another new patch. They are not programmed before. Okay, so this is called remodify write. You read it, modify it in some other place, and write to a new flash patch. So in this case, we don't really need to erase the block. Okay. Okay, so this is about the remodify write. And then multi-level cells, I think we can just skip it. Just like you are going to represent more kind of bits in one floating gate. So you need a better way to differentiate different labels here. Okay, so QLC just mean like you are going to decide like 2 to the 3 bits. Oh, sorry, this is MLC. MLC is 2 to the 3 bits. So triple level cell, so you need to represent 3 bits, and QLC is 4 bits, so you need to have 2 to the 4. Okay, so let's move on to the SSD architecture here. So we talk about a lot here, NAND flash cells. Okay, but actually in SSD, like Phison or like Silicon Motion, in most cases, they focus on designing a controller, because there are several power constraints in NAND flash chips. So they're going to use some like firmware level solution to solve these NAND flash chips. Okay, noting that actually they solve this NAND flash chip issue inside the SSD, because this is an SSD, and outside SSD here is device driver. This is part of kernel, but most of solutions will be inside the SSD. So this FTO, you can think about, this is a firmware inside the controller, okay, inside the SSD, and the controller around the firmware. Okay, so there are 2 main blocks. One is called flash translation layer, and the other is called memory technology device, or MTD. Okay, so the first and the critical thing is about the sequential write constraint. So actually, SSD solves the sequential write constraint by using the address remapping. So SSD also uses same concept of the like virtual memory stuff. Okay, so there are virtual memory, you can think about like logical block address to physical block address stuff. So let me give you an example. If this is a NAND flash block, so block 1, and then there are several patches inside. So this is one patch, and the logical block address is called 500, and the physical block address is called 800. As you already know about like virtual and physical, is about virtual address is what user program or like what kind of application can know. So this one is a virtual logical block address. A virtual is for the like users or applications, and the real address or the physical address on the SSD is called physical block address, and both can be different. So LBA 500 can be mapped to PBA 800. Okay, so now we are going to update LBA 500. Okay, so a better way is, as we say, remodify write, right? We read out this LBA 500 patch and we modify in some place, maybe in this DRAM, like translation table here. There's a data buffer, so we modify in the data buffer, and then we write back to the NAND flash chips. So we modify, and then we write back to another block. So because this block, the latest one is here, so this patch, before writing this patch, it is empty. So we can write the new data to this patch. It doesn't really need to do any erase. Okay, but the case is about actually this one to this one. This one is PBA 800, and maybe this one is PBA like 1201, like here 1201. So if we are going to let if we don't want to let the user to know this kind of stuff, for example, we don't want to let the application know the constraint to aware of the constraint inside the SSD. Then a better way is we don't change the LBA. I mean, for the applications, for the user, they still use the same LBA. But the difference is about PBA. We remap the PBA from 800 to 1201. Okay, and the case is about if we are going to do this kind of remapping things, we need something like patch table, right? But this is SSD, so we are not using patch table. What we are going to use is about the things called SSD translation table. So actually inside the SSD, inside the DRAM of the SSD, there is also a place to put the translation table here. So this translation table will keep track of the mapping between each LBA and PBA. So with this design, actually, for the application, for the operating system, actually, they don't really know what is the constraint inside the SSD. Okay, they even will feel like maybe SSD just like hard disk drive. They can support like the ePlace update. Okay, and this is all because SSD FTO controller helps to cover all this stuff inside the SSD. So no one knows. I mean, no applications know what's going on inside the SSD. But the only things they are going to know is actually they can use the same LBA to do any stuff. They can directly update this LBA, and they can still get the right data because the SSD FTO will focus on help to remapping this kind of pageant stuff. Okay, and actually, this stuff will have another good thing is about, as we say, like we move the data from this patch to this patch, and the prior patch actually we will not erase it directly, right? Because if we are going to erase this patch, we are going to erase this whole block. So inside the FTO will mark this patch as an invalid patch. So there's just a big change inside the table. So maybe in the table, we will say like, hey, actually this patch will be an invalid patch. There's only a big change here. But the problem will be, if there are a lot of this kind of embedded patches inside the SSD, then we are going to do the garbage collection. Otherwise, we don't have enough space to store more new data, right? So when we are going to do the garbage collections, the same things, we need to erase the data. But for example, if we are going to do the garbage collection on this block, and this patch is still valid, but the rest of them, for example, they are all invalid. And before doing the erase, we still need to move the NAND flash patch to other place. So this will also need the address remapping. So running garbage collection inside the FTO will help to maintain the mapping table. So for the application, actually, they don't really know the SSD is doing a garbage collection or not. Because all those kind of stuff, they are covered by the FTO. And FTO will not really notify our operating system or application to say, hey, I'm not doing a garbage collection. No, FTO will just do the garbage collection at the time that FTO feels like it is time to do the garbage collection. Okay, so this is a good stuff because you just plug in the SSD, you just insert the SSD in your server, in your PC, in your notebook, and the operating system doesn't really need to do any change. Even your application, you don't really need to know what is the constraint inside the SSD, and the controller will help to handle most of the cases. Okay. 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 So the agent translator will update the translation table, and then we'll get the data from NAND flash patches again. Okay. So to get the data from NAND flash patches, actually we need this kind of memory technology device, so MTD. And you can think about MTD just about to get the data from NAND flash chips. So the FTO will ask the MTD to know about how to get the data, maybe what's the protocol of the read and write. So MPT will control this kind of data reading and writing things. And the other, the address translation, garbage collections, or even the wheel leveling, we can use, they are all handled by the FTO. Okay, so because we don't have more time to talk about the SSD in detail, so we'll have another course in the next semester, but I can give you some brief idea about, as we point out, like each patch, I mean, has their own kind of lifetime, because SSD cells will be worn out if the electric layer becomes so thin. And one day, if it is not possible to lock the electrons inside the working gate, then these cells will be dead. So when these cells becomes a bad cells, then if there are, sorry, one more patches here. Okay, here. So if there are too many cells in this patch becomes a dead cells or like a bad cells, then this patch cannot be used, right? So a better way is, let's make all the patches, all the cells be worn out at very close time. Like, for example, if all the cells, we can only write like 10 times, then we don't want to that a few of them reach the 10 times, but the rest of them only write like 1 or 2 times, right? So the where labeling is going to label the where. The label means we are going to distribute all the wheres to all the cells. So what we are going to do is to do our best to make all the cells to use up to like 9 times or even 10 writes. So all the cells will be worn out nearly at the same time. And this is what wheel leveling is going to do. Okay, so actually wheel leveling is also controlled by the FTO in the controller. The FTO will say when we can do the wheel leveling, and wheel leveling actually is a combination of a lot of garbage collections. Okay, so garbage collection and wheel leveling, usually they will be combined together to do. Okay, so this is about SSD. Okay, so question? Okay, so next on, we'll talk about the block device driver. Okay, so the main idea behind the block device driver is, as you see now, you have hard disk drive and there's SSD. And hard disk drive and SSD, they show different characteristics. Okay, but if you are a user, you don't want to know you are not using hard disk drive or SSD, right? Because if you are going to make sure, okay, there are different kind of SSD, there are NVMe SSD, PCI SSD, and also hard disk drive, there are hard disk drive, there are SMR drive, there are also a lot of different drives, and you are going to give them different kind of management there. Okay, so it will be super tedious to do this kind of management. So a better way is about, let's do a abstraction, let's do a virtualize there. So user doesn't really need to know what kind of device you are now accessing to. We don't really need to know what is the characteristic inside SSD, the hard disk drive. So block device driver is a layer that doing this kind of device virtualized things. Okay. Okay. So maybe we can like cover 10 and then come back later.
我想请问因为就是他会说有这个 sequential capture，所以他会有这个 read modify write。
对。
那他 modify 的时候是找另外一个 block 去 modify 它的 flash page。所以它会需要一个转换，就是 logical block 和 logical。那这个转换是
另外一个 page。另外 page
是会有，就是在 SSD 里面还会有这有一个敌人是这个原因吗？
对，
那就是它里面还有这个就是还有一个 address transition，那这两个 transition
这是软体，这是 firmware 的 code， 然后这是硬体的区域。
那为什么要分两个？
因为这是就好像我们有 virtual memory 的 manager， 也有 patch table， 所以这个 translation table 其实就是放那个资料结构而已。就那张表而已，但你要怎么去运行它，知道对，你要怎么找，它就是靠这个软体去找它。对，就是这个 CPU 就会跑这个 软体，所以这个可能是一个 C code，然后去找这个资料结构。那这个资料结构可能是一个array 或者是 list 之类的。
所以会有这个 garbage collector 是算是一种就是在查找这个演算法时候会用到的资料结构。
对，就是这些都是演算法，然后这边讲的都是它实做出来，它可能它的那个function长什么样子，这种的叫什么名字这样子。
是啊，
没问题。
只是一个指标，这样子。
我想询问一下，这张图，老师上课是讲说，只要高电压的时候，然后电子会被打进去，然后所以这边就会比较多电子，然后所以它的那个它的这个闸极电压就会变大，然后我想询问一下，这部分是跟这个 VGD 跟 VSD 有差吗？因为我想说，为什么它这边会做？
我觉得这个感觉，我想一下哦，应该说，我觉得应该这样说，就是它如果今天有电子进去的话，那我要读出资料，我需要比较高的电压去激活，就是这个梯形集成里面的电子，它才有办法产生电流。所以我觉得这个讲的不太正确，但是讲的其实是我那个 read 的时候要给多少电压值。
哦，所以这个是 read 的，
这其实是 read 的电压值，对。但是这因为是比较久，我觉得这个比较是，因为这比较概念性，就是说它这边其实只是说 那个 read 的话要比较高的电压才有办法读出里面有资料，那这个可以用比较低的电压值，至少要2伏特就读出来，因为毕竟它里面本来就没有资料这样子。对，这个只是个示意图。对，
我那时候我在想说，是因为这个3伏是这个VGD 的电压，然后导通之后才这个变低的原因，是因为它是在读这个 VSD 的电压。不确定这样理解的。
我想一下哦。我想一下哦，2伏特这样子的话，
对啊，就把那个设的，然后就要出这个，会叫这个。
这个我不确定，但我觉得因为这张图其实是网络上都会有这张图，但我的理解应该是说，这里用2伏特的话，它其实是就可以读出，就可以让它产生电流值经过这边，因为它2伏特足以做到这件事情。只是说，通常因为它这个是浮动的，就是它可能每个 cell 都会稍微有点不一样。那它是用一个固定的2.5伏特作为一个分界点，因为2.5伏特它在2伏特这边的话是可以通过电流的，但是2.5伏在这个地方它是没办法产生电流的，因为它这个地方它里面的电子数比较多，所以2.5伏它激发出来的电子无法构成就是电流。然后这个3伏特我觉得比较像是说，如果要让它可以通电流的话，这边需要到3伏特以上，它才会帮它激发出够多的电子产生电流。
所以老师的理解是，因为它里面有资料，所以它才会需要比较大的这个导通电压才
应该是这样说，因为它里面有知道的原因是我们前一次有给它比较高的那个电压，然后激发出比较多的电子进半导体。那 P 呢就被激发出来之后，它剩下的电子就比较难被激发出来。那这时候如果我还用一个比较低的，像是这个2.5伏特去的话，它激发出来的电子就会比较少。相对来说，如果我前一次并没有给就是 program 的那个高电压的话，我用2.5伏特，我比较有机会去激发出比较多的电子出来。
我加一个电压。
对，所以它这个其实是因为这边是前一次有被高电压 program 过，所以第一半导体已经很难再激发出电子。如果还用更小的伏特的话，那这边是因为我前一次本来就没有打过，所以2.5伏特我本来就会激发出2.5伏特该有的那个数量。
所以像这样没有导通的话，就读不到值，然后这样就读得到值。
对，主要导通就是它会在最下面有一个就是感应的，就是 read 的那个 current 的 sensor， 然后可以知道说，这边有电流。
所以不确定是不是因为那时候
对这我不确定。
因为当初在学电子学的时候，有想说我就想说概念会不会有点像原先要先透过这个 VGD 导通之后，然后因为它导通了，所以之后就直接可以走这边 VSD，所以它才会降低。
这我真不确定。
好，
对，不好意思。
会不会？然后想问一下老师，他为这边写就是打进打出而已。
打进打出，对。
对，然后我确定他读的时候是直接 check 这个 source 本卷的，
就是对他这边其实是一个叫 Beeline 的，所以他这样会接到，就是他其实是，我觉得这样看比较好一点点。这样，他其实是这边是 Beeline，所以刚刚那张图你要把它转这个角度，然后它的 Beeline 啊，它最后面会连接那个 reader 的 sense amplifier，然后去检测说这条 Beeline 到底有没有电流产生。
哦，
对，那像刚刚讲的，如果它中间就截断的话，那它电流就没有那么强。反正它会有一个 read 的那个 sensify 的那个 threshold，知道说到底有没有中间有个点是断掉，有没有足够电流的。对，
不是，因为我那时候看我上面的知道之后，然后跟这边的图有点连接不起来。我不确定这边为什么这边是5，然后这边是0。假设这边是0，因为我这边是接地的意思嘛。
这边是对，这边就
我想说这边接地，那这边又给零伏，可是这样不就是直接短路了吗？
哦，没有，这个给的是那个 P 型半导体的，这个是那个 B-line 的，就是这里是接 B-line，这边会有一条线接 B-line，然后这边是 P 型半导体的，对，所以它这边其实是这边是会接这个状况，这个地方会接5伏特出来，
这边是接5伏，我知道，可是
对，
那下面这边是接地吗？还是这边是最后下面是？
我想一下哦，我懂你的意思，
我想说这边是0，这边又接地，那这边不就直接短路了吗？
我觉得这边可能不是真的是0，它是一个相对来讲比较小的一个电压值，就是可能因为这边想表示的其实是说，这边假设要 program 顶进去，所以它这个不是电压，它这个应该是一个比较小的电压值在这边而已。对，但这边想讲其实比较像是说，这边的话概念其实是，如果我今天要把电子把它打进去，那如果我在横向这边会有一个足够的就是电位差产生的话，那它电子会因为这个电位差而被推到解离那个地方去，它就没办法过的。对，所以它这个只有像它在 program 的时候，我前2个不想打，我只想要 program 后面2个的时候我才会用。那至于这个我不确定，但是我感觉是它应该会给一个非常小的电压值在那边，对，就是不会是5伏特这样。
因为我看原先是这样子，然后都是1.9，然后那照理解来说，它这边变高了，所以它这2个的都，它的电子都被打比较多。对，那为什么这边2个变0，这边2个就不会变？
因为它电子变比较多的时候，如果我它这2个其实是这条线，我这条线如果给一个相对来比较大的电位差的话，那我这边电子就
所以这边会冲的比较快。
对。
然后如果是0的话，就会往上冲。
对，就0的话就是一个很小的电压值，所以它不会影响到这个上去的条路。
所以这个其实也要够大。
对，没错，它是抑制电压，它要调到一个够大的值，就是让它几乎不会有电子跑进去。对。
那我了解是那然后我这边就是主要是看写入嘛。
对，看写入。
那这边是2.5的话，就是变成这边是2.5，然后这边不够，让它直接下来是。
不好意思，这边2.5是这边是
这边
2.5，对。
那这边2.5的话，它的意义是
2.5的话是用来读资料而已，因为我2.5的话，我觉得这边就激发少量的电子出来，那至于它能不能构成一个电流流下去，那是看我前一次有没有打电子进去，因为如果前一次有打的话，我平板里面所剩的电子就比较没那么好被激活，所以我2.5伏特很有可能就激活不了太多。那如果我前面没有打的话，2.5伏特我可能可以激活比有打的时候还多一点。那他们就会算说怎么样可以 2.5伏打下去，里面如果没有电子的时候，刚好可以有电流产生。
哦，所以这2.5是取决于这个，
没错，是取决于 P 型机子的特性。
哦，
对，所以他们要去 tune 那个值。
哦，所以这个2.5是固定的。
2.5点的，对，就是看不同 SSD 它会有，对。
哦，所以读就是看它的，主要就看它的穿隧电流会不会形成。
对，没错。
好，这样。
好，谢。Hi.
So,
Yep.
Father, currently applying to master's programs, especially in the UK, and the deadlines are like kind of coming up. And they ask for recommendation letters. And since I'm applying to a master's that sort of relate to operating systems or have courses that like sort of build up on it, I was wondering if you write recommendation letters.
Yes, no problem. But like, what's the deadline?
Accurately,
Accurately.
beginning of December. I can send you all
okay.
the details though. So
Okay.
even today. So you can get a look and
But I think the only thing I need is about the draft because like yeah, and this draft maybe you can include maybe I think there are several parts. The first part is about like maybe you have different courses and a high score you get it, and then for this course what you learn from this course, and then maybe the project what you learn in this project stuff,
Yep.
and I can help to organize and yep.
perfect. I'll send all of that to you as soon as I can.
Great.
Thank you so much.
哎，没问题。
哦，对。
好，谢谢。小。哦，谢谢。
我想问一下，就是 SSD 不是一个 block device 吗？
对啊。
那就是他怎么知道哪些档案要还是不要？他的 controller
他不知道啊。
那这样的话，那他应该要维持一个，假设他1TB 的 SSD 嘛，那他资讯量就永远是1TB，是这样吗？
我觉得应该这样说，就是你刚刚问的那个问题，应该是说，如果还要知道也不是不行，但他会需要透过做系统给
对，我知道
的。
Linux 是有一个什么
对
东西是可以跟他讲的。
对，但是如果
假设
没有那个的
这东西
话，他不知道。
那这样的话，假设我 OS 假如我 SSD 里面已经还有很多东西了，
对，
那我从 address 开始写，那SSD controller 势必要做一些把资料搬到其他地方，
对，
干嘛的嘛？
对他来讲就是一个 page 一个 page 这样搬，他并不知道里面是什么东西。
SSD 的容量是不是可能比实际上标还大？不然他要做一些
对，
搬来搬去，
因为它会有一个就是那叫什么来着 over provision 的区域
啊，
所以它是会有一些没有用到的 block 是专门让你做这样搬来搬去的，对用途的。
那这样的话，就是我刚才说的那个最极端的 case 是从最底的 edges 往上写。
对。
那这样它资料会不会就可能 SSD 的实际容量是它原本标的2倍？等于对吧？那这样
它只有10%，通常1%到10%而已。
对吧？那这样就是为什么不会可能坏掉，然后就资料就不见了？
你说从小开始往上写，
对吧？就是，
但是你写完一题就没有了。就是如果它是一颗 SSD 的话，就是对他来讲，他就接一堆 BIO，然后从小开始往上写。对啊，
好像也
对啊，他就是反正他就这么多容量，然后他看到也只有每次都是可能如果从 OS 进来的话，它就是一堆512，然后他在 SSD 的DRAM会稍微去把它 buffer 一下，让它变成一个 patch，然后就直接写那个 patch。所以对他来讲，他看到就是一直都是4KB，然后就这样搬来搬去。对，然后最多就是用到一体，用完
反正就是它实际容量可能会比标的还大一点，让它可以搬。
大家可以不要说到很满的时候搬的时候效能
不会到2倍，
不会到2倍，通常不会差那么多。对，
那我再想一下
好，
谢谢。
我想问一下，在读取的时候，他这边说，就假如说他 floating gate 没有 airflow 的话，它这个比较不会导通，那是因为它的 pixel 这里面它的 airflow 总量会比较少。
没错。因
为我之前查有一种说法是说，它这个输入的电压会跟那个 floating gate 里面的一些电子抵消掉，有这个说法。
电压会跟电子抵消掉，这个我不太懂，可以再稍微讲多一点吗？
我那时候看的资料，他只有说会有抵消的问题，所以导致它那个电池比较 没办法会吸到这一块。
结论那样是对的，但中间这块我不太确定，就是电压跟电子抵消问题。你说这边如果2伏特的话，然后这边如果有电子的话，它实际上apply 到 P 扫圈可能不会是2伏特。
对，
这我不确定，但我自己的理解就是看文献的理解，其实是就是这边直接给2伏特的状况下的话，它可以激发的电子数会比较少，所以它比较难去。因为里面如果有的话，代表是它前一次有被 program 过，那它一次就用比较大的电压去激发出比较多的电子了，那你现在用比较小的去激发的话，它势必觉得比原本预期的更少一点，那更少的话，它就没办法成为足够量成电流是这样，我理解本来这样，但是你刚才讲那个结论上来是没错，可是对我不确定它是不是
像这个原理可能有一些问题。
也不一定是问题，搞不好它真的也是有可以达到这个效果这样子，对，其实我不确定。
那我回去再仔细查一下。
好，谢谢谢谢。
那我想到一个问题，就是，因为有资料想要写进去，然后把它打进去之后，然后它的这个导动电压上升，然后所以会不好流通，会就是一般的电压会没有办法去流过它，它就读的值会是0。
对，
那可是不是有存资料就是要去读它，这样子会更，可是读出来会是0，还是这个0的意思是
0的是意思其实是它读到的电流值比较小而已。
所以它0的意值就是，电流值少，然后你可能中间这一条里面某一个地方有资料这样子。
哦，没有，你如果要读这个 page 的时候，其他人都会给一个非常高的电压值，所以其实他并不会知道里面到底有没有值。因为你这个 V 给5.0，就像我刚才提到一样，不管你有没有写东西，你给 V 只要给5.0，它这边都一定会导通。因为它给的电压值够大，所以其实他并不会知道其他人有没有，他只能知道是你现在读这个 page 的这个位置是它有还是没有。因为它没有的话，它只有下半部下来，那它的总共的电流值就会比较少。所以他其实会知道说，你这边总共如果每个都可以导通的话，最多大概就是电流值在多少。那你今天如果其中有一个 page 没办法导通，对某一个 bit 没办法导通的话，那它的电流值可能会只剩多少？
所以这个0的意思，0跟1的意思，
因为其实是在跟大家说，这里面其实1对，但其实不是他真的实际上收到的，他实际上收到应该是那个安培，对，然后他也不会是0，他可能会是一个相对量比较少，就是这2个相比就比较少一点点的。
哦，就是读出高低电压的意思，然后高低电压再去找资料嘛之类的。
高低电压里面其实就代表是，假设它这个地方是高电压好，那代表这里面就是1跟1，它这个如果得到低电压，代表里面是0。就是其实1跟0这个概念只是要让使用者知道它是1跟0，但对于 SD 或者是对于 NAND Flash 来讲，它其实就是底部电子差别而已。
哦，我一开始想说1是有资料，然后0是没资料，我开始
1是有资料，0是没资料，你要这样想也是没错，就是这个状况也是，就概念上是没错的，但是这里的话应该是讲的是，就是我知道，讲反了，对，你刚才讲的对，就是一的话应该是，我想一下1的话是这边有收到电流值，所以这边的话是电子在 falling gate 里面是比较少的状况，对，所以它里面是没有资料，没错。然后你刚才问的问题其实是一个蛮有趣的问题，就这件事情啊，falling gate 里面有值还是没值，跟它对应到是1还是0这件事情是可以被firmware去configure 的，就是一般正常来讲的话，1代表的是1通常代表的是就是，如果你看那个图的话，1通常代表的就是底面是没有值的状况，通常，那0代表的是通常是里面有值，那至于值多少，就是看你是 MLC 还是什么时候。那这件事情呢是可以透过 firmware 去改变的，就你也可以定义说，现在这个1代表的是有值，0代表的是没值，也可以。对，所以这件事情并不是固定，就是说一定是1代表什么，0代表什么。对，只是说以这个例子来讲，如果摒除1跟0的话，实际上应该要是这边电流代表是我收到的是高电流值，这边代表是我收到的是低电流值。那低电流值代表的是我这个 cell 里面有资料啊，高电流代表是里面没资料。
然后后续就是交给机器机顶。
对，就firmware你要定义你是1还是0，这件事情都可以，反正只要 align，就是你这个firmware是这样写的，那我所有的 cell 都要可以这样定就可以了。对，没错。
谢谢老师，
谢谢。 All right, so let's come back. Okay, so before diving into the block layer, let me quickly go through how CPU access the peripherals. Okay, so because like usually in our system, CPU needs to access like the register, for example, in the SSD, so to do some management or even to CPU to access like the keyboard kind of data inside the register, those kind of stuff. Okay, but how to do this kind of addressing things? So there are two ways. One is called port mapping, another is called memory mapping IO. So this is a CPU. And like for port mapping IO, because it is called isolated IO, so it is about the IO address space and memory address space, they are separated. Okay, so this is the memory address space and this is the IO address space. Okay, so for example, if you are using a 32-bit systems, then the memory address space, like you are using a 32-bit to do the memory address. And then IO address, you will depends on another address space. Okay, and if we are going to support this kind of isolated address space, we need extra instructions. So in this scenario, CPU use low store instructions to access the memory address space. Okay, and this is the directions that usually general CPU access the memory. But in and out, this is another set of the instruction. So CPU needs to support this in and out instruction to access the IO device if they are going to choose for, if this CPU is going to access the IO device in different address space, then we will need in and out instructions. Okay, so usually this case, usually we're used for this kind of like timer, interrupt controller, this kind of low bandwidth kind of device. Okay, so usually it's about, because if you are going to do this kind of stuff, you need extra complex management for this in and out kind of stuff. But you can save a little bit, of the memory address. What I mean memory address is about the address space. So come to think about, if you are using a 32-bit systems, then you can only address in 4 GB. So it doesn't really mean about how many DRAM you have now. It is about you have 32-bit for your CPU. So your CPU can only address up to 4 GB. And it can be, some of them can be in the DRAM and some of them can be in the IO. So this case is called memory mapping IO. So like this, if this is the 4 GB address mode, then part of it can be IO address, part of it can be the DRAM. Okay, so I need to clarify here, as the address space is not equal to the DRAM space. So address space is only for the CPU, how much of the address it can use to address it. And then this addressing, it can be DRAM or it can also be IO. And this is called using the memory mapping IO. Okay, and this one, if you have a 4 GB, then you have a 32-bit, then you can use a 32-bit to address the memory address space. And the IO address, we will use another address space to address it. And because you are using another address space, so you need extra instructions. You need to let your CPU to support different instructions. And using the right-hand side memory mapping IO, both of the IO and memory address, you can use the low store instructions. So for example, if a CPU is going to access like NVMe driver stuff to access the NVMe SSD, and NVMe SSD inside there are several registers to do the control stuff, and the register will be mapped to this IO address. So CPU with this IO address can directly get the data from the register inside the NVMe SSD. So it is fast and you can increase the bandwidth. But the point is about, if you are not using a 32-bit system, you need to sacrifice part of the address and use for this kind of IO device. Okay, so this is about the memory mapping IO stuff. Okay, so there is another concept is called like DMA. So DMA is about to transfer data directly between memory and IO device without CPU's interventions. So what does this mean? So usually you have CPU and like you have IO device and memory. Okay, so if you are going to get the data from IO device, then who is going to keep track of the moving progress? If there is no DMA, then a CPU needs to set up the range and move the data from IO to memory, and then to monitor if it is finished or not. And then for the second IO, CPU needs to do it again and again. So CPU, so using the CPU, actually, it will waste a lot of CPU time to monitor, to set up this kind of IO stuff. So a better way is to use a technical DMA. So DMA usually is a lightweight controller. It is also a kind of CPU, but it is a microcontroller. It is a micro CPU. So DMA is about like this. When we are going to move the data from IO device to memory, CPU will tell the DMA about, let me set up the range of the data you are going to move. For example, CPU will tell the DMA controller to say, hey, maybe let me move like 1 GB of data. And the starting point is from which address, and the offset, the length will be 1 GB. And then DMA will start to move. DMA will read out the data from the IO device to the DMA's register, and then move it to the memory. So DMA will take care of all this kind of moving stuff. And after CPU do the configuration on a DMA controller, CPU can do other stuff. Okay, CPU doesn't really need to wait here. Doesn't need to wait synchronously for the IO completion. So CPU can just do any other stuff than waiting for the movement. Okay, so this is how DMA work. Okay, so just about to a proxy about to help CPU to move the data. Okay. Okay, so those are the like hardware part or CPU part. So let's move back to the kernel part. So this is a split view of the kernel IO stack. So this is applications, and under here, those are hardware, right? So there are different hardware devices. There are keyboard, mouse, SAS, USB, PCIe bus, those kind of stuff. So for each of the device, actually, there are device controller here. So there are the keyboard device controller, mouse device controller, blah, blah, device controller. So anytime when you see a controller, it means like there is a micro CPU there. So a micro CPU there means we are going to run some software stuff like firmware. So keyboard device driver inside, it will run the keyboard firmware. Mouse device controller will run the mouse firmware, and a hard disk drive, SSD, those kind of controller, they will run their own firmware there. Okay. But the stuff is about then how the system, how the operating systems can interact with this kind of controller. Okay, how to send the request from the system into the hardware. So the thing is the device driver. So device driver works as a bridge between the operating system or our host systems and the device. Okay, so you can see like this, there is a keyboard device controller. So it means we also have a keyboard device driver. So device driver can talk to the device controller, or device driver can interact with the device controller. So for each device, there are more like mouse device driver, as the SAS device driver, USB device driver. So different device driver can talk to their related device. Okay. And then device driver is also part of the operating system. Okay, so device driver is part of the system because device driver is also a kind of the kernel code. Okay, and firmware is not a kernel. It's not in the kernel. So firmware is inside the device. So firmware is not a part of operating system, but device driver is part of the operating system. And there is let me check. I think I didn't put it in the slides, but there is a very interesting analytics data here. Like I think it's kind of 70% of the Linux OS source code, they are about device driver. So like your scheduler, your memory manager, your CPU scheduling stuff, actually there's less than 30%. But device driver, because there are a lot. Each device, they have their own device driver. And then maybe not only one device driver, maybe they have two, because you have NVMe driver, you can have the PCI driver, you can have the SATA device driver, So there are way more device driver you think in the OS kernel. Okay. Okay, but yeah, for the device part, actually we split into two kind of devices according to their characteristics. One is called block device. The other is called character device. So block device is addressable in device-specific chunks called blocks. Okay, so it is more like this kind of stuff. Just like if this device is going to get more data, like more sequential data, or like more a bunch of data from a device, it works like the block device. So just like your hard disk drive, usually when you are going to read the data from a hard disk drive, you are going to read out a bunch of data or a block of data, right? So because like your file is in like 2 megabyte, 4 megabyte, or even 1 gigabyte. So usually you are going to export a block of data, and there's called block device. So like CD-ROM, storage device, they are all block device. Okay, so because you are going to read out a block of data, so it is possible for you to do the seeking. So you are going to read maybe in the middle of this block or like in the head of this block. So you can, so block device also support like random access. Okay, and in most cases, block device, they are mounted as a file systems. So like if you have a hard disk drive, then you will mount a file system on this hard disk drive, like this kind of stuff. Okay. Okay. So yeah, I think data blocks we'll talk about it later. So it doesn't really need to talk now. So here is about USB driver and SAS drivers. They are all block device. So how about character device? So character device providing access to data only as a stream. So what do I mean for stream? For example, when you are using a keyboard and you type something on a keyboard, you type like ABCD, and then it is a string because the first one is A and then B and then come also like C and D. So they are usually in the bytes granularity. Okay, and also the mouse, how often you click the mouse, this kind of stuff. So they are all about the character device. So the thing is about if the data you are going to access is in a block, like continuous, like 512 byte, this kind of size, then it is block device. But if not, like you usually access them in a byte table, then it is called character device. Okay, so character device included like the keyboard, mouse, those kind of stuff, they are all character device. So because they usually only stand in the stream, so the data transfers rate are quite low because you type on a keyboard and then you need to, for example, if you wait for several few milliseconds and you type another byte there. So usually you will not like the block device needs a super high throughput. Okay, because a block device is about you already know you want to move a super large like block. So you rely on the throughput. But character device usually is about the latency. You don't want to miss each character when you type the keyboard. So it is about the latency. Okay, so in this, I mean, in the rest of this lecture, actually, we only focus on the block device. Okay, because the storage device, those they are all block device. Okay, so block device, character device, they have their own device driver, and device driver is a computer program operating or controlling a particular type of device. Okay. Okay, so when you are using a Linux, actually, you're not really, I mean, if you are a user, not a programmer, then you will not really work with the device driver, right? But it's still possible to access, like, if you still remember, like /device/SDA or like SDB or even TTY1, TTY2, actually they are all block and character device. But in the user label, you can still access them, right? And the reason is like this. So you are a user or like you are applications, and if you are going to open the file, if you are going to access some things in the block of character device, actually there is a thing called device spatial file. So device spatial file used to interact with drivers. Okay, like this. This is a user space, and then the device spatial file is /device/ like SDA-A, SDA-B, or like /like TTY1, like our monitor, TTY2, those kind of stuff. So you can think about this is an interface between the application and the kernel device driver stuff. So this kind of slash device slash SDA, if you mount the file system on it, then it will go through a virtual file system and then a driver and then to the hardware. And if there is no file system, then there is a device driver, and there's a hardware. Okay. So let me briefly recap is about kernel modules, just like device drivers, are a piece of code. So they can be loaded and unloaded from kernel on demand. So device driver, it is also a piece of code, but device driver looks a little bit different from general, I would say like OS kernel code, because it is more constructed. Their structure is quite clear here. So I'll give you an example here is a device driver. So the format here is like this. The structure here is like this. Usually you will have this kind of module init and module exit. So module init, you can think about more like when you are writing a C++ code, there is a thing called constructor and destructor, right? Constructor is when you are running a C++ code, then when you first run the code, and what will the system do for you? What will the code do for you? And this is the same. When you insert a module and you run the module in a Linux kernel, you will first run the module initialization, module -init. And in here, we will just print K to print a like kernel alert things, like hello world. Okay, so kernel runs a function when the module is loaded. It is called a initialize function, and this is using the module -initial like function here. Okay, so the output usually is 0 if it is code successfully. And the purpose here is just to initialize hardware, allocate data structure, those kind of stuff. Okay. And then once when you are going to kill the kernel driver, kill the device driver, if you are going to unload the device driver, so you will then run the module -exit. So the exit actually, usually people are going to free the resource, shut down, and reset the hardware. So here is about you are going to allocate your resource used by this device driver in the initialize part, and then you're going to release it in the exit part. Okay, so mainly device driver, they are composed with these two functions, initialize and exit. Okay. Oh, this is a module license. I think it's not important. Just about to let you know, you can put a license in your kernel code. Okay, so how to build a device driver? Actually, there are several ways. First of all is about to store driver code in your own Linux repository code in your offline, in your PC. For example, if you download the tarball file and if you run the tarball and then to unzip the tarball file, then there are a lot of folders. Then you can put your own driver code in the driver blocks or a driver character, depends on what kind of driver you are writing. And if you are writing a block driver code, you can put it into the drivers/block folder. Then modify the make file in the directory, and then you can run it. So there's another way, it's called build externally. So build externally is about to maintain and build kernel module outside the kernel source tree. Just like you can create a make file by adding like 2 comments, like this kind of stuff. You can just have your own kind of .o file, and then you can compile it to the, you can have your .c file and then compile it into your kernel object file. And then you can directly build it in place. You can build it in your Linux systems, and you're finished. Okay, so for the source tree, you need to upload into the source tree, but for the build externally, you can build offline. Okay, so just to let you know, there are some different way to load the device driver. So for some cases, if you install the kernel, like kernel function, if you are going to install a new kernel object, in some cases, for example, if you change the scheduler and then the virtual memory stuff, in some cases, you need to restart the systems. But in most cases, if you are going to add the new device driver layer, in most cases, you don't really need to restart the systems here. Okay, so here are just kind of some hints to let you know what's going on for when you run the make command here. Okay. Okay, so just want to share with you some interesting when you're doing a kernel programming. So there's a question is about how to access the stat for the current process. So if you still remember, like here, we say like if you are a process, then you are running in a user mode, then it is called the normal process, right? But when this process needs the service, when it needs the always service, it dives into the kernel mode. Okay, and in this case, actually, it is about CPU to change from the user mode to kernel mode, and it still execute on the same process, right? Because it is about the kernel program they share with all the user process. I mean, the top 1 GB, if you still remember, in the 32-bit address space, the kernel space share the top 1 GB of the address space. So when you are running a kernel, it is not about you call another kernel function to run the device driver. It is about you still stay on the same user process, even the same context. But part of the context they switch to the kernel context. So it is possible to access the current state of the current process. So what do I mean? Oh, sorry. That's just about the detail. So this is a user program process data. So the same things, this is a CPU in the user mode. And then we are going to, if we are going to access the kernel module or like the device driver in the kernel address space, it's just about for the CPU to switch to the kernel mode and then to access the kernel address space. So for the user address space part, it still stays on this user process. Okay, so it is possible for the kernel to access the stat for the current process by like this kind of stuff. If you type into print k is the print function in the kernel version. Okay, so there is a called like current structure because it is about the text structure. So you can dot like COMM or like the PID, and then you will return the current status of the current user process. For example, what is the PID for the current process, like this. Okay. So you can get most of the information you can get in the text structures for the current process. Okay. So this is about it. And then, okay, here are several things that in the kernel functions that you need to think about twice before you are going to use them. But the first is about the super small stacks, because like when you're doing a kernel programming, actually you don't have too much of the stack size. Like there's only 1 to 2 stacks. Okay, so this is the things like if you're going to do like a complex kernel code, and then you have a lot of functions to call in the kernel, probably you are out of stack. And the second one is about usually in Linux code, there is a kernel functions at a prefix, there is a double score. So this is usually low-level component should be used with cautions. So actually in kernel, there is also some are in a very low-level things. I mean, like if you accidentally modify these low-level components, maybe it will let the other kernel functions maybe hard to run or like even crash. So you can think about those are like core function that you use inside the Linux kernel. So when you are doing the kernel function programming, you can think about if you are going to really modify this kind of kernel functions in the prefix of the double scores. Okay. And I think there is a very interesting stuff is the third one. It's about do not use a floating point. And floating point support is very expensive in the kernel and should be avoided because when CPU is in the kernel mode, it cannot really use the floating point accelerators. Okay, so if you go to check in the browser to type in the Google about can I use a floating point in the kernel mode and tend to do some computations, and people will just say, if it is possible, please don't do this kind of stuff because you will be super slow. Because when the CPU is in the kernel mode, you cannot really use the floating point accelerator to do the computations. Okay. Okay, so why it is so expensive? Because it just save the floating point registers while switching from the user to kernel mode. So if you really want to use it, then there will be several hundred of seconds to do this kind of mode switching. I would say like context switching things, but the context switching is only for the floating point register. Okay, so this is about the things for the kernel programming. So I think, if I remember correctly, the third hands-on will be related to this kind of kernel programming stuff. So you can just that you have a very brief feeling about how does it feel like when you are going to do a kernel programming and what can you really get after your programming. Okay, so let's move on. So after the device driver, on top of it will be the block IO layer. So block IO layer is between the file system and the device driver. So device driver, we say it is a bridge for the systems and the device. So for the IO layer, you can think about if there is a file system, it is going to access the data on the storage device, right? But actually file system, I mean the file concept will be after file system. So for this kind of device driver device, they don't really know what is a file. Okay, so we need another abstract layer called block IO layer to do the abstractions for the file system and the block device driver. Okay. Oh, sorry. Okay, so let's first do some quick background build up. So for the sector, we say the sector is the smallest addressable unit of the storage device. Okay, so if this is a storage device, then the sector is like this. So the reason to use sector is because at the very beginning, like several decades before, there is only hard disk drive, right? So hard disk drive, we said the track on each track there are several sectors. Okay, so SSD is later on, like there is a later on for the hard disk drive, but operating system is already using a sector. So from the operating system perspective, actually sector is the smallest addressable unit. Okay, so even for the OS, they send the sectors into the SSD. SSD can do the do some operations on the sector and then to rebuild it to the patch and to access it. So it doesn't really have the conflict for SSD use a patch, but hard disk drive using the sector. And the concept behind the sector is just to unify the granularity to access the storage device. Because for some storage device, they lack 512 byte. For some storage device, they lack 4 kilobyte. Okay, so the idea is just about to unify those kind of granularity. And then the second one is a block. So the block is the smallest located unit of the file systems. Because as I mentioned, file system doesn't really know like sector or like inside SSD things. So it needs another things called block. So the size between the patch, block, and sector is usually patch size is larger than block size and then larger than sector size. Okay, so sector is the smallest addressable unit. You can think about like this. And buffer is the things called like this. So it's an object which represents a block in memory. Okay, so block is the things located by a file system, right? And if we are going to use this block, it needs to move into the memory because the CPU only interact with the memory. Okay, so block is like this. When a sector is in the memory, it is called the buffer. Okay, and for data inside the memory, we need some data structure. We need some data structure to describe this kind of buffer. So there is a data structure called the buffer head. Okay, so buffer head in Linux will look like these kind of structures. Actually, there are several fields here. So for example, for the first one is about b-stat. So it is about to identify this sector inside the memory, it is dirty or not. What do I mean dirty or not? When we move a sector to the memory, and for example, when the CPU is going to update, to modify the data inside these sectors, then you will become dirty. Okay, but if the CPU doesn't really write something in its buffer, it only read it, then it will retain non-dirty. And also, it is possible to lock something in the memory. So there is about the stat for lock or not. Okay, and the second one is about a b-block device. So this one is about, because when you are going to read the sector from storage device, probably it can be from like more than one disk. It can be one from hard disk drive, another from solid state drive, another from the other hard disk drive. I mean, they can all be read from different kind of device into the memory, right? So we need some way to link between the device and this buffer. So this B dash block device, this pointer points to the corresponding block device. So for example, this buffer will be pointing to this block device, and maybe the other buffers will be pointing to other block device. Okay, so it's just going to that the operating system can find where is the data. And then there's a thing called B dash patch. So this points to the corresponding patch for storing the block. So because this buffer, you can see like this buffer is from the sector, and this is smaller than a patch. So probably this patch will comprise several buffers inside. So if the buffer is kind of 512 byte, then we can have things kind of 30, 16, oh no, add, sorry. We can have add buffers inside one patch. Okay, so we need some way to identify which patch it is. Okay. And then we have B dash data. So it points to the starting point of the block. So you can image like if we are going to access a block, the first of all is about we'll get this buffer head data structure, and we are going to find the buffer. Where is the buffer? So we'll use a B dash patch to locate where is the patch, and then use this B dash data to find out where is the starting point of the buffer inside this patch. So we can read out the data from this buffer. Okay. And also the size. I mean, it describes about how large it is for this block. Okay. But here are several challenges for using a buffer head, because buffer head is a quite old data structures in Linux. So the key thing is about buffers head plays the role of buffer to block mapping, right? So the thing is about first one is if there is a large and bulky data structure, buffer head is a larger and bulky data structure. So a block is more than a patch, and each buffer is described by a buffer head. So the thing is like if we are going to access like the continuous add blocks in one patch, then we need add buffer heads to describe this add blocks. Even they are all continuous, but we still need to access the buffer heads at times. Okay, so sorry. So each buffer head, you can think about if this is like 1 byte or even 2 bytes, then how many fields there are, then you need to times like the data size, the data format for each of the field. So buffer head, it takes some place. For example, maybe one buffer head is like several 10 or even 100 of bytes here. So in this example, if we are going to access like continuous data blocks, but because one block should have one buffer head, then we need to have a large memory consumptions by using these buffer heads. Okay, so the solution for this one is in 2.6 kernel version, like kernel address space instead of blocks. So in this case, we don't really need this kind of bulky data structures. Okay, and there is a second challenge is kernel should break up large block IO operation into multiple needless buffer heads. So just as I mentioned, what IO operation is if you're going to read out a file, and this file is like 2 megabyte, sorry, it's if it is 2 kilobyte, for example, or even 4 kilobyte, then you need to break these 2 or 4 kilobytes or even megabyte of the operations into several buffer heads, because one buffer head is only 512 bytes. So if you are going to read out 512 kilobyte, then you need 1024 buffer heads to serve for these block IO operations. So a better way is about actually we should maintain a data structure in terms of the block IO operations, not really the block, because the block is 512 bytes. Okay, so a new data structure in 2.5 is included, is called BIO. Okay, so this BIO structure is going to replace buffer heads. Okay, so this one BIO is a block IO request. Sorry, BIO is a block IO request comprise IO operation that are in flight as a list of segments. So blocks belonging to an operation need not be continuous. Okay, I think this is kind of hard to understand. So here is an image here. So this figure shows the architecture of the block IO. So one block IO means it is one block IO request. And for one request, actually, there are different IO operations. So you can think about, for this request, there are one read, one write. And the read and write, they are reading and writing different place of the hard disk drive, for example. So each of the IO operations you can think about is one BIO vector. Okay, so these BIO vectors, they are chained by using the linked list. Okay, so this one, sorry, there's a typo here. This should be one block IO request, and these are several block IO operations here. Okay, so for what IO operations, they interact with one thing called segment. So segment is a bunch of buffer that is continuous in memory. So because buffer is only 512 byte, but actually for patch, it is 4 kilobyte. So sometimes if you have a size between the buffer and patch, then it is hard to position, right? So for example, if you have an IO operation, it is kind of code like 1024 bytes, then actually it means you have two buffer. But in the buffer head, you need two buffer head data structure. But in this case, you don't really need like this. If this is a patch, and this is its patch frame, so the segment means any size, any continuous size inside the patch. So, but we need some way to know what is the data, where is the data. So actually, for this BIO, for each BIO vector, we have maintained 3 fields. One is about which patch it is, and where is the offset, and where is the length. So which patch it is in this patch. So this is the patch frame. And inside the patch, there's 4 kilobyte of the data. So where is the data start from? So this segment start from this offset, like this. This is the patch, and this is the offset. Okay. And with this offset, how much of the data we are going to read out? So the segment size, we can use a length to describe the segment size. Okay, so if we put it all together, so for each IO request, it should be a continuous IO request. And for the BIO, it can work with several IO operations. So this IO operation, this IO operation, and this IO operations, they can be combined in one BIO. And the thing is, file system will help to combine different IO operations together and then to send as one BIO to the block layer. Okay, so here. So actually, there will be a request queue for capturing this kind of block IO requests, and it stores pending block IO requests. So requests are added to the queue by like file system, this kind of stuff, and file system will try to merge those IO operations they are related together. For example, if these two IO operations they are from reading the same file, like they're the same files, and then but this one we are going to read out the first part of the file, and this one maybe in the bottom of the file, but they are not continuous. So for the file system, they will merge them together and then to send into the block IO layer with one BIO structures. So this is the things we call the block IO request. Okay, so I think we can stop here and call it a day and see you guys next week.帮我跟赵平讲一下，请他帮我一下。对。
那这个是所以是后来不用这个东西的吗？
就是比较旧版本的桌项才用这个。
那这个是为什么说 change 这边重要吗？但是其实还有
就是
看不了。
主要原因是因为它现在是一个 block， 它就需要有一个资料结构。
哦，这个 buffer to block buffer 是
就是 对，就是这就是
到底哪个是 memory，哪个是
这个是 memory。
然后这个是 I/O 指挥这个。
这个
storage device。
对，就是把 file system 去分配出来的区间，但也在 storage device 没错。
对，以前说这个意思是说要维持它。
这个意思是说，你今天如果要把这个 sector 拉到机体里面去，或者是好几个 sector 拉到机体里面去好了，那这个地方你会需要有个资料结构去维护，不然怎么知道它在什么地方？因为机体很大，那这个资料结构就是叫 buffer head。但是 buffer head 能做的事情就是你每一个 buffer 都会需要有一个 buffer head，那一个 buffer 就是512 byte 而已，因为它就跟 sector 是同个 size， 在现在的 Linux 里面是这样。
这边是一个
对，那如果今天它是1024 byte 的话，它是连续的，假设它 buffer 是1024 byte，
对，
假设，但是它还是要2个 buffer head。对吧？但是它其实连续的，但它其实可以用一个，但是它现在因为之前的克隆设计，所以它就是要2个。所以它如果今天是个连续的一个程序，它可能是10个或者是20个的话，那它就是要10个、20个这样子的 buffer head，但是它其实都是在一个连续的空间里面。对，对，所以这个地方就是在讲说，既然这样的话，我们其实不应该拿一个固定的size 来看，它应该是用 request 来看。
那这个 BIO 的
这个
是就之前那个 page table 那个嘛，就是说 page
没有不一样。这个地方只是说，因为它这个是建立在 page 这件事情上面的，所以系统里面本来就有 page。
因为这个是 physical 的。
对，这是 physical 的，就是在机体里面的状况。然后因为它这个是一个连续的空间，所以它如果需要去定位出这个连续空间是多大，
意思是说是什么？
就是你把以这例子来讲的话，你把这个 buffer sector 丢到这个地方来，这边每个都是一个 page frame， 那你怎么知道你的 buffer 是在哪一个 page frame？
你说哪一个？
对，
那这个 offset 是
offset 就是一个 page frame 是4KB，但是它里面可能资料可能小于4KB。它可能就是什么1024，那这样的话我怎么知道是哪一段的1024？对，
这里是1024B 吗？
假设对，对吧？
然后 length 就是1024，
就是1024，对。
然后这边的话可能就是
那个 offset， 就是多远这样子。因为你只知道这个 page 开头在哪里而已，但你不知道后面到底资料放在什么地方。
这边2048B 这样子。
对，类似这种。对。
就是所以是一个，就是一个这个系统里面是有很多这个 BIOS structure。
对，
所以它就是每个都是分配下来，然后再比过来。
就是这我刚才讲比较快，其实它应该是说，就是你 user 下指令给档案系统，然后假设你要读一些资料，然后档案系统会根据现在 user 下的情况去把他觉得相邻的这些 request 把它合在一起。就例如你可能同一个使用者读了一个很大的电影出来，但你可能只读了前半段跟最后面那个部分，但你还是在同一个电影里面，那它可能是存在同一个硬碟里面，那档案系统就会帮你把它全部集合在一起，作为一个 BIO， 就是一个 request 送给 block layer。但是呢，因为刚刚说的它是同一个电影，但是它是前面跟后面，所以它一定是在分开的2个位置上面。所以呢，一个连续的位置它需要有一个 BIO vector。所以它刚才是2个分开的位置，所以它需要有2个，就是 BIO vector。好，那要几个 BIO vector 就是看你要读东西有多大，然后有多少不连续。那基本上一个 BIO vector 代表就是在一个 page 里面一个连续的空间有多少。对，所以像这个example 其实就是说，它如果这个连续的空间是这么大，可这么大我怎么知道是在 page 里面什么位置？所以它需要有 offset 跟 len 去做一个定位。然后 page 就是基本上因为你把资料读到 memory 上面，本来就会可能会有放在某一个 page frame 里面去。那放在哪个 page frame 的话，我就要记录下来，这样我要读的时候才把它读出来。
那它有可能会发生，就是在同一个 page 里面，然后有2个区。
同一个 page 里面有2个区块，你说
分前面一小块，然后中间断掉，后面又一小块。
有可能。
会要2个 vector 还是？
对，因为它这个定义是 a chunk of buffer that is continuous in memory。所以如果不是 contiguous 的话，它就要2个 vector 去。
所以就是它就是用一个 segment 去看。
对，它是用 segment 去看。
所以就是它有可能会指到同一个 page。
对。
应该是。
好， 见。
想问就是像现在的，
等一下哦，我先关一下。